Okay, heat transfer and entropy changes. So we know that water freezes at temperatures below 0 degrees Celsius. How does the entropy of the water change? Is this process spontaneous? So second law of thermodynamics says for any spontaneous process, the entropy of what increases? The universe, right? The universe. I forgot that there was a fill in the blank on this slide. Don't remember doing that, but there we go. The entropy of the universe increases, not just the system. So we have to look at the system and the surroundings. And so if we're talking about water freezing, we'll consider water to be the system, and everything else in the universe is the surroundings. So the change in entropy for the universe is the change in energy for the system plus the change in energy for the surroundings. So the system's entropy can decrease as long as the surroundings entropy increases more than the system decreased. So why does freezing water increase the entropy of the surroundings? Well, we know that freezing is exothermic, right? How do you make water freeze? You cool it down, right? Or sometimes it's helpful when you're doing these endothermic, exothermic things to think about the opposite. Well, how could I make ice melt? I could heat it, right? Put heat into it, it'll melt. So then the opposite process is heat coming out. So freezing is an exothermic process, which is causing energy to go out from the water, and entropy is the dispersal of energy. So the energy was in the water, and in the process of freezing, the energy left the water and went out into the surroundings, where it is more dispersed than it was in the water sample. Does that make sense? Everybody okay with that? So here we have the change in entropy for the universe. The system went way down, because going from a liquid to solid, the particles are more ordered, they have less ways of moving, but the surroundings entropy went up more. So freezing of water is not spontaneous at all temperatures. And the magnitude of that delta S surroundings is temperature dependent due to the dispersal of energy. So the greater the temperature, the smaller the increase in entropy when that energy leaves the water. So the higher the temperature of the surroundings, the less change in entropy there is when energy is released into the surroundings. So entropy, there's too many E words. Entropy is a measure of energy dispersal per unit temperature. Joules per Kelvin, which happens to be my initials, are the units for entropy. So the change in entropy for the universe, if this, the change in entropy, not energy, entropy, energy. At least I didn't say enthalpy. The change in entropy for the system for water freezing is negative. The change in entropy for the surroundings is going to be positive, but it's going to be positive and large at low temperatures, positive and small at higher temperatures. And so at some point, the positive delta S of the surroundings is equal to delta S for the system that's negative, and it's a wash, right? So here's the low temperature graph, I guess you could call it. And here's the high temperature. So the change in entropy for the system is the same, but now the change in entropy for the surroundings at higher temperatures is less. And so the sum of these is a negative change for the universe. meaning this is not a spontaneous process. And we know from experience, right, that water does not spontaneously freeze at 75 degrees Fahrenheit. So when a system exchanges heat with its surroundings, it changes the entropy of the surroundings. That's what we were just talking about with the water freezing, energy leaving and going into the surroundings. So we can use Q-sys to quantify the change in entropy of the surroundings at constant pressure. The change in entropy of the surroundings will be proportional to negative Q for the system. And again, Q is heat. So it's proportional to the amount of heat gained or lost by the system. So if we have an exothermic process where Q-sys is negative, when we plug, and this is always very confusing for students. So it's proportional to negative Q-sys. That does not mean that Q-sys is negative. It means it's proportional to the opposite in sign of whatever Q-sys is, -1 times. So if Q-sys is negative, I don't know what happened to that Y, then that's going to equal a positive number, right? So then delta S will be positive. An endothermic process decreases the entropy of the surroundings. So if this is a positive number, then the change in entropy for the surroundings is negative. Everybody okay with that? One of the things I really enjoy about this class is we can go at a slower pace. I don't have to do half a chapter in an hour. And so, if we have questions, we can all just stop and get those things settled before we go on. So the magnitude of the entropy change is inversely proportional to the temperature. Higher temperature, less change in entropy. Change in entropy for the surroundings is proportional to 1/T. And in the previous slide, we said that this was also proportional to negative Q for the system, so we can put those together. Delta S for the surroundings equals negative Q for the system over T. If we have conditions of constant pressure and temperature, so the temperature is not changing, pressure is not changing, then Q-sys is equal to the enthalpy change for the system, delta H. So then we can get to this equation here. So consider the reaction between nitrogen and oxygen gas to form dinitrogen monoxide. Calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees C. So we just learned an equation for that. The change in energy for the surroundings is equal to negative delta H for the reaction over T. So we have delta H here, right? So it's negative of delta H. So delta H is positive 163.2 kilojoules. And what unit do we need for the temperature? We need to have it in Kelvin. So 25 plus 273 is 298 Kelvin. So negative 163.2 divided by 298 gives us negative 0.54 times to 8 kilojoules per Kelvin. Yeah, it needs to be in joules. And we can kind of see why. Most entropy changes are going to be quite small, and so they're much nicer numbers in joules. So this is going to be 500, negative 548 joules per Kelvin for that temperature. Determine the sign of the entropy change for the system. Pardon me? That's a good question. So we do see that we have an endothermic process happening here. But then we also have this business of going from 3 moles of gas to 2 moles of gas, right? And so they're both actually telling us the same thing, right? So if you go to fewer moles of gas, that's less disordered, negative entropy change. Positive entropy change. Everything else is backwards compared to entropy. No.
So you're going from 3 moles of gas to 2?
3 to 2 would be a positive change in entropy. It's because
some of it's going to the surroundings.
Oh, okay. Isn't this fun? It's so fun. So all these other things, we've got this negative, positive thing, right? And that's so entrenched in my brain. So entropy is the measure of disorder. So if it becomes more disordered, then the change in entropy is positive, and if it becomes less disordered, it's negative. So the change in entropy, looking at the moles of gases, would be negative, and what would the change in entropy be looking at this? Positive. Well, it's constant pressure and temperature, so then delta H is equal to Q. So that's where that equation comes from. So the change in entropy for this system, it's going from more moles of gas to less moles of gas, so it's negative. Yeah. So delta S is negative. So then, what will the change in entropy for the universe be? Negative, because this one is negative and this one's negative, and so when you add them together, you're still going to get a negative number. So is it spontaneous? No. Not spontaneous.
So the entropy is negative because even though it's absorbing energy from its surroundings, there's less states of energy.
Yes.
Okay.
So the change in moles of gas trumps the endothermic business.
Gotcha. Would it trump it every time there's a difference?
That's an excellent question. I think it would. Because having fewer particles is a bigger change than the amount of energy. Yeah. Yeah, so wasn't that fun? Embarrassing. Okay, do biological systems contradict the second law of thermodynamics? We think about it. By taking energy from their surrounding and synthesizing large complex biological molecules, Plants and animals tend to concentrate energy, not disperse it. How does that work?
As far as creating, how it contradicts.
The second law of thermodynamics says the entropy of the universe is increasing.
Yeah, they don't because they have different intermediate molecules that come from making larger complex molecules like water and carbon dioxide.
Yeah, so they're taking oxygen and hydrogen from water and carbon and oxygen from carbon dioxide, and they're making it into big complicated molecules, which would be more ordered, a negative entropy change. Right? Can't remember the answer to this one either. Well, obviously they don't, right? Because laws like this, you can't break them, right? So if the entropy change for the biological system is negative, what must be true?
Entropy must be increasing somewhere else.
The entropy has to be increasing somewhere else and has to be increasing more than it decreases in the system. Right?
That'd just be the general heat that we give off.
A lot of it is the heat. Yep. So, we're all just here running our, Krebs cycle and all of our other things, and we're giving off heat into our surroundings. So this is a new one. Stop.